Seems like we primarily have people here remotely today. So I'm going to get started. So homework number 7 on chapter 10 is due on the 20th. Homework number 8 on chapter 11 is due next week, Thursday, on the 27th. So we're going to talk about the muscular system, the motors of the body. So the muscular system is what moves your body around. It's all your muscles, but also the tendons that connect your muscles to bones and things like that. So we'll talk about the 3 types of muscle tissue: smooth, skeletal, and cardiac. We'll discuss the functions of skeletal muscle. We'll look at the microstructure of skeletal muscle, the macrostructure of skeletal muscle. We'll look at the 3 different types of muscular actions, which are concentric, eccentric, and isometric. We'll describe the roles that muscles can assume. We'll discuss the factors that influence the force developed during muscular activity. And we'll understand the relationship between power output and velocity of contraction of a muscle. So muscles are the active component of the musculoskeletal system. They're what actually causes things to move, whilst bones are the passive component. And they have a unique capacity to actively shorten and produce tension. So they generate force by shortening, and this provides stiffness to joints for skeletal support and also controls the motion of the skeletal system. So you have passive rigid segments that are actuated by muscles, which are active and can actively change their length. And when they get shorter, this generates tension. There's 3 types of muscle tissue. There's smooth or visceral muscle, which is smooth in appearance and is greatly extensible. You can stretch it a lot. This is the walls of blood vessels, hollow organs, like your intestinal tract, things like this. This is what pushes stuff throughout, squeezes on stuff, moves stuff through your digestive tract, things like that, helps move stuff through blood vessels. Then there is cardiac muscle, which is unique to the heart. It is striated in appearance, and it forms the walls of the heart. So it's similar to skeletal muscle in that its structure is it's not smooth. It's got bundles of fibers, but it's uniquely, it's different in that it can be constantly and repeatedly contracted, because your heart is always pumping. So your cardiac muscle has to always be active, always be contracting and expanding. So it has unique properties because of that. And then there is skeletal muscle. This is striated in appearance, and it's controlled by the voluntary nervous system. While the smooth and cardiac muscles are more controlled by the involuntary nervous system. Not completely, but more controlled by the involuntary nervous system. So we're going to focus on skeletal muscle because it's the primary thing that generates movement of the body. So the functions of skeletal muscle are things like movement and posture maintenance. It attaches to bones and it controls the motion of joints. It lets you move around. It also produces heat. about 75% of the energy used in muscles is released as heat. It's one of the many things that produce heat in your body. It also acts as protection. It helps absorb energy at joints. And it helps pad your skeletal structure. And skeletal muscle also assists with the venous return of blood. So the return of blood through veins is assisted by being squeezed along by the skeletal muscles, where the veins have a bunch of basically one-way valves in them. And then as they get squeezed along, the blood moves back towards the heart. Now, skeletal muscle is made of a bunch of muscle fibers, which are single muscle cells. Each fiber is very thin and long and is covered with a thin membrane called the sarcoma. Sarcoma, yes. And then it is encased in endomysium, which is a connective tissue sheath that anchors fibers to other fibers and to the tendons at the ends of the muscles. So here's an image. So we have a bunch of individual fibers that are surrounded. Each individual fiber has a membrane of sarcolemma, each white fiber, and then it is surrounded by and connected to other fibers by the endomysium. And each individual fiber has a set of sarcomeres in various zones, and these are what allow for the process of actual active shortening in muscles. So the interaction between, in the sarcomere is what actually contracts. The interaction between the myosin and the actin, there's a thick filament and a thin filament in here. Basically, you can send energy into this. It's triggered by nerve signals, and the myosin kind of pulls along the actin and shortens the muscle. And the cross segments of the microfilaments have different patterns in different parts of actin and myosin filaments, and the I band and the A band, and the M line in the middle. So each fiber consists of hundreds of myofibrils. So these myofibrils are part of one fiber. This is surrounded by a sheath and then connected to other fibers with connective tissue. Each fiber consists of hundreds of myofibrils, which are aligned parallel to each other and run the entire length of the fiber. And the striated appearance comes from repeating light and dark bands in these myofibrils. And the sarcomere, the basic contractive unit of the striated appearance, comes from repeating light and dark bands. The basic unit of muscle that contracts is a sarcomere, and they're attached in series at the Z line here. So there's a Z line that attaches each sarcomere to the next. And then it has, in each sarcomere, there are actin, which are thin filaments with one end attached to the Z line, the other end overlapped with the myosin, which are thick filaments, which are attached to each other in the middle, in the central portion of the sarcomere. And they have cross bridges here that project to potentially link with the actin. And you can link and unlink in such a way that pulls the actin and the myosin fibers together. And you can do that repeatedly to keep pulling them together. So a fascicle is a bundle of 100 or more fibers. And then there's the paramecium, which is the connective tissue sheath encasing a fascicle. And a muscle is made of bundles of several fascicles. And the epimecium is the connective tissue sheath encasing the muscle. This is sort of the macrostructure. And a tendon or aponeurosis connects the muscle to the bone. And this is an extension of the endomecium, epimecium, and paramecium that transmits muscle tension to the bone. So this, we have each individual fiber has myofibrils in it. They're surrounded by sarcoplasm. And the sarcolemma surrounds the entire fiber. There's a bundle of fibers that form a fasciculus. And these are bundled together to form the whole muscle. So bundles of bundles of bundles is sort of, so each fiber is made of myofibrils, and each myofibril is made of myofilaments with actin and myosin thin filaments. And there's the nucleus for each cell. So this is one cell in a muscle fiber. And then there's the endomecium between fibers, the epimecium, which is between fascicula, and the paramecium, which surrounds the fasciculus. The epimecium sort of on the outside. And all of those merge together to form the tendon. And the muscle in the attached tendon will pull on bones as the muscle shortens or lengthens. And to reduce friction, there's connective tissue between muscles. There are bursa, which are synovial fluid-filled sac pads over bones or liquid to allow your tendon or muscle to slide over the bone or ligament. And then there's a sheath around the tendon, which is a tube wrapped around the tendon that helps allow things to slide. And muscle tension is equally applied on each attachment. The origin is the proximal attachment and the insertion is the distal attachment. We don't, but both ends of the muscle pull in, but one side is tied to the bone, the other side is tied to the far side of a joint. So here's the muscle, then there's tendon, which is collagen fibers made from the connective tissue of the muscle, and it transitions into the bone where they intermesh with the fibrocartilage at the surface of the bone. Collagen fibers from the tendon intermesh with the collagen fibers of the fibrocartilage of the bone. Now, muscle fibers can be arranged in a couple of ways. The muscle's line of pull is the direction of the resultant force at the attachment. If all of the fibers are aligned with the line of pull, this is a longitudinal muscle. So these are fusiform muscles or strap muscles. That's the shapes you can have for these. And then pennate are when the fibers insert at an angle to the tendon. They're not aligned with the tendon. So you can have unipennate, bipennate, and multipennate. So here's a strap muscle. It's just a long strap. Here's a fusiform where it bulges in the middle. You can have unipennate where they're at an angle, and bipennate. And there's sort of a trade-off between longitudinal and pennate muscles. Longitudinal muscles are all the fibers are aligned. And all fibers are aligned. They're called longitudinal and muscles that are not aligned. So the advantage of pennate is you sacrifice the amount of distance that you can compress for more force. The longitudinal muscles can cover a larger distance, but in exchange, they have less force, which we'll cover later. So when a muscle develops tension and pulls on its attachments, there are three types of this action you can have for a muscle. You can have concentric, where the active muscle shortens. This would be like if you're lifting a weight, a bicep curl, the upward swing on a bicep curl. The active muscle is your bicep. The torque exerted on the limb is in the same direction as the limb is rotating. An eccentric is when the active muscle lengthens. This is when the torque exerted on the limb is in the direction opposite the limb rotation. So bicep curl on the way up is concentric, on the way down is eccentric, because the tension is resisting, the weight of the torque from the weight you're holding. And then isometric is where the active muscle stays the same length. The torque is exerted on the limb, but there's no limb rotation. That's like holding a weight. Now, when muscle activity happens, there's a change in limb mechanical energy. When muscle tension exerts a torque on a skeletal limb, for concentric, the muscle is doing positive mechanical work. The concentric torque increases limb angular velocity or gravitational potential energy. For eccentric, it's doing negative mechanical work. The eccentric torque decreases limb angular velocity or gravitational potential energy. And for isometric, it's doing no work because nothing's moving. There's an isometric torque produced, but no limb angular velocity or change in potential energy. So these are some concentric muscle activities: the upward portion of a pull-up, the upward portion of a push-up, the forward portion of throwing a baseball here, the forward part of this swing, the speeding up portion. These are eccentric: the downward portion of a squat, lowering in a bicep curl, the slowing down portion of a running step, and again, the end of a tennis racket swing where it's slowing down. And then isometric, you're not moving. Now, we can also talk about agonists and antagonists. Antagonists, yeah. An agonist creates torque in the direction of referred joint action. This is called the prime mover or a protagonist. So this is the muscle that is a muscle that's active concentrically is the agonist to the action occurring. So for elbow flexion, the biceps brachii is the agonist. Or if I'm doing lifted upward bicep curl, the biceps brachii is the agonist. The antagonist creates a torque opposite the referred joint action, or torque opposite another muscle that's referred to. So a muscle that's active eccentrically is agonist to an action occurring. So the triceps brachii on the other side of your arm is antagonist to elbow flexion and to biceps brachii. So muscles come in pairs. One will act as the agonist or protagonist. The other will act as the antagonist. The muscle contracting in the direction of motion is the protagonist. The muscle active eccentrically, the concentrically active muscle is the agonist or protagonist. The eccentrically active muscle is the antagonist. Now, other muscles can act as stabilizers. A stabilizer creates a torque preventing joint action of the agonist or a torque opposing another external force causing motion. This is called a fixator or a supporter. This is a muscle that's active isometrically to help stabilize a joint. This is what you're doing when you're, holding yourself steady while lifting a weight. And a neutralizer is a muscle that creates a torque preventing some undesired action of another muscle. So this is a muscle that's active isometrically to prevent something that you don't want happening from happening. I'll do a little bit more. So let's talk about how muscles activate. The basic unit of muscle tension development is the sarcomere, and it is stimulated by a motor neuron. So the motor neuron innervating the muscle provides a stimulus, and the general process of tension development is cross bridges of myosin attached to actin, pull on the actin, release from the actin, reattach, and repull. So that's how muscles get shorter. It's like tug, let go, tug, let go, tug, let go, tug. Now, the tension produced is the sum of all the various cross-bridge pulling forces. Generally, the more cross bridges that are attached, the more pulling force you have. For concentric activation, the muscle shortens. The actin and Z lines slide towards the middle of the sarcomere in the direction of cross-bridge pull. For eccentric activation, the muscle is lengthening. The actin and Z lines slide away from the middle of the sarcomere in the direction opposite of the cross-bridge pull, but they're resisting this process. So the way muscles work is a muscle can be activated with a single twitch response. So a single stimulus from the motor neuron, where the cross bridges briefly attach and release. You get a short duration, quick rise and fall in tension. That's a twitch. Or for longer duration force, you use tetanic response. The tension is developed in muscles from an increased frequency of the stimulus by the motor neuron. So a single pulse from the motor neuron gives you a twitch, and then repeated pulses lead to longer stimulus, greater force. So the tension remains from the prior stimuli when the next stimulus arrives, and they sum with each successive stimulus, and tension rises to a higher value than from a single stimulus. So a single twitch response gets this much stimulus, but if you get repeated pulses, you get an increase, then another increase, then another increase, then another increase, and it stabilizes up here. And that's what happens in general when you're doing a longer force and a higher force. And multiple factors can affect the maximum force the muscle can develop. So the first is the cross-sectional area. The bigger the cross-sectional area, the wider the muscle is, the more force it can generate. It produces about 30 newtons per square centimeter of cross-sectional area. Now, the length can also have an effect. There's a contribution from active and passive components of a muscle. Basically, the more a muscle, there's like a length that's optimal for generating force, but there's also some passive effects from the stretching out of the muscle. And the velocity of the muscle shortening or lengthening can affect the strength. Eccentric is greater than isometric, which is greater than a concentric. We'll go over this as well. So the muscle contractive force, if for fibers in series, the force doesn't increase, but the length change possible does. For fibers in parallel, the force does increase, but the length change possible does not. So if you need more length change, you need fibers in series, or longer fibers. But you don't get any more force from longer fibers. If you need more force, you need more muscles in parallel. So the cross-sectional area depends on how the fiber is arranged. If they're in longitudinally arranged, you can take a single measure perpendicular to the muscle fiber and to the line of pull of the muscle that includes all the fibers. However, in a pennate arrangement, the fibers in the line of pull aren't aligned, so you have to take several cross sections to include all the fibers. But this does allow actually more force. So here, for example, you have more cross sections. You get more force from this. So the same volume, you can get a bit more force from a pennate muscle, but you can't get as much length. So it's a trade-off. So to do a cross-section through a pennate muscle and perpendicular through its line of pull. So this cross-section of AA would miss these fibers and these fibers. So more fibers would be applying force. And the amount of force produced depends on the length of the muscle when it's activated, but it's not like a simple linear relationship. There's active tension from the interaction of actin and myosin. And there's a maximum overlap, which provides maximal tension. That's the resting length. If it's shorter than the resting length, opposite actin overlap, you get fewer cross bridges, reduced tension. If it's longer than the resting length, you have less overlap of actin and myosin. Again, fewer cross bridges, reduced tension. But there's also a passive force from stretching your muscle. Now, the minimum contraction length of a longitudinal muscle is shorter than that of a pennate muscle. If the resting lengths are the same, the longitudinal muscle can create tension through a greater range than a pennate muscle. So the active tension, at the resting length, you get the maximum tension. If it's shorter, you get less because the actin overlap. If it's longer, you get less because the actin interacts less with the myosin. There's also passive tension, however, from the stretching of various connective tissues. And that gets more the longer, the more the muscle is stretched. So the tension developed in a whole muscle is the sum of the active tension and the passive tension. And maximum tension is developed when a whole muscle is about 120% of its resting length. Looks something like this. Because there's a peak in active tension here, and maximum tension is a little bit higher. You go too far, you start relying too much on passive tension, and this is where you're getting into risk of damage. Because this is just muscle and stuff being stretched. And that means if you change the length of the muscle in question, you can get more force. So here we have a shorter length for the muscle, you get less force. Here, this setup has a longer muscle length, and so you get more force. And I think that's where I'm going to stop for today, and I'll go over all this stuff about the active process again on Thursday. I'm going to stop sharing. I will see you all on Thursday. Have a nice day. I will end the meeting.